Okay, let's get started. I'm going to do an example or two today with conditional probability, but I also want to talk today about independence in a bit more detail. So the idea of independence is, the technical definition is that the probability of B given A equals the probability of B. That's the more technical way of saying it. The way we usually describe it is that knowing that one doesn't have an effect on the other. Knowing that this event happened over here doesn't affect the chances of this other event happening. So in other words, if I tell you that A happens, it doesn't change your probability of B happening. So this is different from mutually exclusive. Mutually exclusive, if you remember from the last section, said that the two events can't happen at the same time. This would be saying that the probability of A and B is 0. That's the idea of mutually exclusive. Is saying that if A happens, it's possible for B to happen. Well, that means it's not independent, because if I know A happens, then the probability that B also happens is now 0. And so we can actually use, when we look at these tables, we can actually use this to test for independence by using this definition. And so based on these two probabilities, if they're independent, these should be equal if they're independent. In other words, what we're saying, if the two events are independent, is that if I want the probability that they had a low grade, then knowing which school they came from shouldn't affect that probability. It shouldn't change that probability. But it does. If I tell you they're from engineering, physical sciences, the chances that they got the low grade goes up. It changes your guessing game of, if I'm telling you this information, does it change your chances of them having a low grade? Well, in this case, it does. So those are not independent. So let's look at another example of this so that you can see that in action again. So there's your definition. And we're asking, are the events of male and left-handed independent? And so what we're going to do is we're going to pick one of these and we're going to find the probability of them. They like to ask a question like this as a free response. I've seen it quite a few times. So let's look at one. Let's call male A and left-handed B. And so the idea here is we want to find the probability of B, and we want to find the probability of B given A. And our question is, do these probabilities match? Well, the probability of B is the probability of being left-handed. So how many of these do we have being left-handed? Well, we have a total of 7 of these out of 50, which is going to be 0.14. So we have 7 out of 50 are left-handed. Now, probability of B given A, this is what we're testing here. The probability of B given A says, given that A has happened, so given that they're male, so let's look out of all the males, that's 23. Out of all the males, how many of them are left-handed? So if I tell you the person is male, what's the probability that they're left-handed? Well, 3 of them are. So we have 3 of these out of 23. And that's about 0.13. So they're pretty close to each other, but if they're independent, these two probabilities should be exactly the same. If they don't match, that means they are not independent. So the other way of phrasing that, is that if I say I'm thinking of a person, can you tell me whether they're left-handed or not? You have that probability in your head. But if I tell you, okay, the person I'm thinking of in this group is male, if they're independent, that shouldn't change your guess of whether they're left-handed or not. But it does ever so slightly. It says that they're less likely to be left-handed now that I told you that they're male. If they're independent, then telling you that they're male shouldn't have any effect. So that's why these probabilities not matching means the events are not independent. My usual example for independence is flipping a coin and rolling a die, or individual dice rolls. So if I tell you the first one is a 6, well, individual rolls of the dice are independent. Knowing that the first roll was a 6 doesn't change your probability of the next roll. Or it doesn't change whether you pick heads or tails on the coin flip. Those events are independent of each other. If they weren't independent, then me rolling a 6 would somehow alter what you think the coin flip is going to be. But they don't have anything to do with each other, so they're independent. So notation-wise, we're looking at finding a randomly selected person who reads the USA Today. So USA Today is A. Also reads the New York Times. So we're finding the probability of, if I know they read the USA Today, that's the thing that I'm told. That's the thing that I know already. And I want the probability that they also read the New York Times. So if they read the USA Today, so given USA Today, what is the probability that they also read the New York Times? So we're finding probability of New York Times given USA Today. So that's going to be, in probability notation, it's going to be the probability of B and A over the probability of A. But I think it's easier to think about it just in terms of the given, instead of trying to memorize a formula. So the idea is that out of the given, that's the thing you want to remember, is that the given goes on the bottom. So I already know that they read the USA Today. So I'm only looking out of this group that reads the USA Today. So how much reads the USA Today is 40%, 0.4. So out of all those people who read the USA Today, how many also read the New York Times? And that is this area right here. So out of this circle, we want this area. So that's going to be the 0.05. So in this case, it's not a multiplication of anything. That's what I heard some groups discussing, was some multiplication. It is out of the people that you're already told about, how many fit into the other groups that you're interested in. So out of the people that already read the USA Today, how many also read the New York Times? That's what you're finding with a conditional probability. So out of 0.4, we have 0.05. So that's going to be, that's 1 and 8. So that's going to be 0.125. All right, this is a pretty common question as well, where we're looking at false positives and false negative rates. And so we want to think about what probability we're finding first of all. So what is the probability that an athlete who tests positive actually took drugs? So if we have this small percentage of athletes who have taken the banned drugs, but we have a test that has a false positive rate of 1% and a negative rate, false negative rate of 0.5. So the idea is that a false positive rate that's really high in a situation where only a small percentage of the people have whatever we're looking for is actually going to have some weird results for us. This probability is going to be higher than we think. So the idea is that we're finding the probability that someone who tests positive, so we are given that they test positive. We are told that they tested positive. That's the information that we know. Given that they test positive, what's the probability that they took the drugs? So that is the probability that we're finding here. The best way to do this is to make a tree diagram. So that's what we're going to look at here. So we want an athlete. And the easy thing to know about the athlete, we have two choices, is the test coming back positive or negative. That's one of the variables we're interested in. And whether they took the drugs or not. Whether they took the banned substances or not. Well, the probability that we actually have is the probability that they took the banned substances. We don't actually have the percent of athletes who test positive or test negative. We have false positive and false negative rates. So those are going to go within the smaller branches. So we're going to say drugs, no drugs. And we're going to write out those probabilities. So the percent that took the drugs, the banned drugs, is 2%. So that's going to be 0.02. Which leaves the percent that don't take the drugs to be 0.98. Everyone else. Then we're going to find within those groups whether they test positive or test negative. So we have positive, negative, we have positive, negative. And then here's where our false positive and false negative rate comes in. Because false positive well, if you have a false positive, that means that you get a positive even though you don't fulfill the conditions. So a false positive is the probability of a positive given no drugs. So drugs complement. So given that you didn't take the drugs, you still got a false positive. And so that rate is 1%. So this is where the 0.01 goes in the no drugs but still tested positive category. So that means the rest of the people who didn't take the drugs, they test negative, which is what should happen. And then our false negative rate is 0.5. So that's our probability that we have a person who took the drugs, who took the performance-enhancing drugs, but then still tested negative. So that goes in this branch. 0.5% is going to be 0.005, which leaves the rest of them to be our people who tested positive and took the drugs, which is what should happen. So now we multiply and get the ends of the branches of the tree. All right, now that we have this probabilities, check this out. I think this answer is going to surprise some of you. Here we go. Probability that they took drugs given that they tested positive. So we're looking out of the people who tested positive. How many of them actually took the drugs? That's what we're going to end up doing. So the people who tested positive, well, that's going to be this group and this group. Those are my people who tested positive. People who tested positive and took the performance-enhancing drugs, and the people who tested positive and did not. So we've got 0.0098 plus 0.0199. That is 0.0297. So that's what goes on the bottom. What that means is that just under 3% of everybody, of all the athletes, test positive. So what's the probability that they actually took the drugs? Well, the people that took the drugs are up here, 0.0199. So that's going to be our fraction. That's what we're going to divide by. And when we divide that, we get 0.67. And so good news and bad news here. The good news is that our test is more often than not detecting someone who actually took the drugs. The bad news is that it's also turning out a third of the athletes we have in our group that test positive didn't actually take the performance-enhancing drugs. And that's because of two factors. Number one, we have this false positive rate. We have such a high false positive rate. And number two, we have a very high group of people, a very large group of people who did not take the performance-enhancing drugs, which starts to inflate this number to be bigger than it needs to be. And I think this is a relevant example because you might have heard people talk about positive testing rates and false positive rates. So if you have a test that has a large false positive rate, then getting tested again might be a good idea to do. Again, most people will be in this category and be in the clear. But within that category of testing positive, that can be relevant